This video is going to go through an example that's actually kind of cool. So we're going to work with a cone, so z squared is equal to x squared plus y squared, and on this cone there are 5 rotations about the z-axis as the height along the z-axis goes from 0 to 1. So we need to sketch a figure and then find a parameterization. So let's go ahead and start the sketch. Let's try that again. And so we're going to sketch this. So in our standard x, y, z plot, I'm going to put x along this axis, y along this axis, and z along the vertical. Okay. And I'm going to draw the edge of the cone here. So it's going to look something like this and like that. And then I'm just going to extend this a little bit. And then we have the cone up top. Okay, and then on this thing we start at 0, 0, and then we kind of wrap around this thing 5 times. So that's 1, 2, 3, 4, 5. Okay, and so then this would be necessarily 1. Okay, so we need to find a parameterization for this, right? Well, where do we begin? My answer? Start with the equation that you know. Z squared is equal to x squared plus y squared. Okay, and now we need to think back to the parameterizations that we've done in the past, right? So the parameterizations, okay, x squared plus y squared, okay. To me, when I see this, this looks a lot like r squared from when we were talking about cylindrical coordinates. Okay, so maybe that's just what we need to think of, is try a parameterization using cylindrical coordinates. So I need r, theta, and z, and then in each of those I need a single parameter. Okay, well, this equation is actually really nice because it just tells me that z is equal to r. So really this just becomes r, theta, and r. So I've eliminated one parameter, z, and it's just I'm down to 2 now, r and theta. I need a way to link those. Okay, I should actually also mention here that since z is within 0 to 1, r is within 0 to 1. Okay, and we know z is between 0 and 1 because of the given information. All right, let's stop though. So if I want to look at theta, right? Well, let's think about the values that theta will take on. Well, it's going to certainly start at 0, but then we wrap around this cone 5 times. So as I look at it in the xy plane, theta is going to go from 0 to 10 pi actually. 5 times 2 pi. Okay, but now I need a way to reconcile these two range values. It'd be nice if I could get them into, say, a single variable. Okay, the way I'm going to do that is by introducing a new parameter that would be common to both of them. I'm going to introduce a parameter t, and I'm going to say t is going to be within 0 to 1. Okay, what is nice about this is it maps directly with r. So instead of using r, I can use t. However, to resolve theta and t, what I'm going to do is I'm going to say theta is equal to 10 pi t. And my claim is that this puts theta, or that this parameterization will allow theta to go from 0 to 10 pi, but allow us to only use the parameter t. Maybe pause the video and just make sure that that makes sense to you. Alright. Then, with this parameterization, we can go ahead and introduce the parameterization for the whole figure. Okay. If we're using cylindrical coordinates, the parameterization would be, for x, it would be r cosine of theta, and r here we're using t instead. Oh, let me erase that. t, and then cosine, and then theta is 10 pi t. Y is r sine of theta, so 10 pi t. And then z is just z, which is r, which is t. Okay, and then this would be t is within the range of 0 to 1. Okay. Now again, if you want to check your answer, I always recommend going to GeoGebra and do that 3D view. I have that set up and it is in the file called Tornado. Okay, so it does show the cone, and then you can see we wrap around the cone once, twice, 3 times, 4 times, 5 times. Okay, and you can certainly change the view on this as well, and that should complete this exercise.